Please join me in welcoming our next speakers, Alexander Marvey and Brad Slaybaugh.
Thank you, Mark. Hi, my name's Alex Marvey, and this is Brad Slaybaugh. I'm a senior consultant at Google Cloud Mandiant, and Brad here is a manager for both the incident response team. And today we'll be covering UNC3886. This is a Chinese espionage group that we've been seeing become more and more active over the past year. And what's unique about this situation is that we've been seeing this group specifically target solutions within victim environments that are not able to have EDRs deployed to them. In our case specifically today, we'll be speaking to hypervisor technologies and firewall technologies that, when used in tandem, allowed the attacker to stage information and pull it out of the client network. From another key point being that as time has been going on, we've been noticing a consistent amount of sophistication growing on these Chinese Nexus threat actors. So we've been seeing them active since late 2021 across both the APJ region and the Americas. And in, again, this case, we've seen them actually utilize multiple 0 days in this attack path alone, utilizing a mixture of proxies, backdoors, and traffic redirection utilities to move in and out of the network and circumvent your traditional net flow. Additionally, we see them exploiting and abusing hypervisors. In this case, there was a 0 day within the ESXi hypervisor that allowed abuse of a legacy protocol, if you will, for unauthenticated interaction with the guest machines without the need for anything other than the hypervisor's credentials. Lastly, we see a unique and considerable focus on the anti-forensics used by this threat group. We see a disabling of logging services, selective removal of log entries that are associated with the network indicators of this attacker, the flipping of bits to disable security mechanisms, and time stomping, along with time stomping across multiple operating systems just to hide their activity. I'm going to hand it off over to Brad, and he'll talk to the FortiGate environment.
Yep. So as we conducted these investigations, we kind of noticed a similar attack path that the attacker was taking, really focused on stealth and establishing a foothold on these technologies that just don't have very good detection components to them. So this usually started with them compromising a public-facing firewall manager server. In this case, we'll talk about the FortiManager that we saw in a couple of instances. From there, they would use firewall management scripts to leverage a 0 day on connected FortiGate firewalls to this FortiManager to install a backdoor on those FortiGates. From there, they were able to hop over to the virtualization layer, mainly focused around vCenter and ESXi, which Alex will touch on later in this presentation. So starting off with compromising edge layer devices, this really was where the attack, based on our investigations, this was the earliest point of evidence, were these public-facing firewall management devices. So looking at that top portion of the attack path, what we saw was the attacker install multiple backdoors on these edge layer devices, one of which was a Python-based backdoor, which we refer to as thin crust, which we'll touch on in a little bit, and also using an open source malware known as Reptile that the attacker also used as kind of their primary backdoor on these devices. They were very redundant. They installed it across the FortiManager, the log aggregator, FortiAnalyzer as well, to really make sure they had a strong foothold in the environment. So as we kind of touch base on the various firewall ecosystem, the attacker used a variety of backdoors and malware families, 4 of which we'll talk about today. The first is thin crust. This is a Python-based backdoor that the attacker embedded into legitimate Python code on that FortiManager device. Castle Tap is the backdoor that we observed on the firewalls themselves that provided pretty much standard backdoor functionality. And we saw the attacker primarily using these backdoors to interact whenever they would come back into the environment. Table flip is a traffic redirection utility that the threat actor used after some of our clients started to implement remediation efforts to kind of limit access to that public-facing FortiManager or that firewall management server. This allowed them to still kind of persistently access that FortiManager device, and we'll touch on that in a later slide here. And then, as mentioned, Reptile was kind of their go-to backdoor, open source backdoor that's available on GitHub, compiled it for the various Linux flavors and distros for these devices. So going back to the initial access here, as mentioned, based on all of our investigations, it led us to this public-facing firewall management device. As we began investigating these devices, we started to kind of compare a known good device to what was compromised. I mean, this is where we started to see some differences in some legitimate-based Python files and how we found this thin crust backdoor. Additionally, as we were looking at binaries on this file, we noticed a couple of files that were not in that clean image. Analysis of that kind of determined it to be that Reptile backdoor, that it's a full-featured backdoor for the attacker. And as they had compromised these devices, they would then abuse firewall management scripts to push out the castle tap backdoor to the firewall fleet that was connected to this FortiManager device. And they made use of a local 0-day on these devices to get that installed, and we'll touch on that in a little bit as well. So let's start off with thin crust. So on the right, we kind of have a quick snippet of the Python code that was appended to a legitimate Django web framework file on the firewall management device. Provided the attacker with standard capabilities to execute commands and transfer files to the device. They made use of the HTTP cookies field in the HTTP header whenever interacting with this device and sending it RC4 encrypted commands to be able to execute on that device. The attacker was able to then add in a specific API endpoint so that they could interact with this backdoor. So if we look at the top right, these were the API endpoints that were available on a legitimate FortiManager device. On the bottom right image where we see that compromised urls.py file, the attacker added a specific API endpoint that they could then use to access that device. What's also important to note is the attacker added a Django decorator to essentially bypass authentication for this particular API endpoint. So anybody that would hit this API endpoint did not need to authenticate first before accessing this backdoor. The next thing that we want to talk about is table flip. So, as our investigations progressed, one of the things that a couple of our clients had was public-facing firewall management servers. So the first step they took was to really restrict access to that, only allow the necessary devices that are on the internet to be able to communicate with this. So what the attacker did to bypass this was they used a utility known as table flip. So table flip implemented IP table rules on the FortiManager device to basically for the one port that was open on the FortiManager device, it would contain a specialized command. And within that command, it would reroute traffic internally on the device and causing the FortiManager to beacon back out to the attacker's infrastructure. Now, in order for the attacker to accomplish this, they had to already use a compromised FortiGate device that was still in the environment. So they came back in through that firewall to deploy table flip to allow the attacker to have easier access back to that FortiManager device. And then, as we mentioned, whenever they compromised the FortiGate devices, they used a local 0-day. So as we were investigating this activity, we happened to come across a suspicious directory traversal command in these firewall event logs. Looking at the command that we see here, we can see that the attacker is abusing an FTP and TFTP service for this execute wireless controller command. The attacker was able to use a directory traversal attack to replace a legitimate file on the FortiGate device. In this particular instance, they replaced the file lspci in the /bin directory here. So the attacker was able to download their own malicious code to the FortiGate device and replace a legitimate binary on that firewall. The attacker can then execute that that backdoor or that new malicious code with a diagnose hardware lspci command. So we saw this through logs as well as in memory samples of FortiGate devices that we've analyzed during these types of cases. And with that, I'm going to turn it over to Alex, and he'll dive into the compromising of the virtualization layer.
Thanks, Brad. So as Brad mentioned, once the attacker established a foothold within the environment, we'd see them directly connecting out to, let's see, yeah, right up there, the vCenter machines. And now, once compromising a vCenter machine, the attacker actually had the ability to harvest a service account that is created automatically when connected to an ESXi hypervisor. And this would be the VPX user. So with this service account level access, the attacker would proceed to access the ESXi hypervisor, install persistence through a vSphere installation bundle, and then use another exploit, in this case UNC3886, there we go, to access and execute commands on guest machines without any need or any authentication checks made at the guest machine level. Looking at the malware families that were identified across the hypervisors and the guest machines, we have virtual PITA, which we saw across the ESXi host and Linux machines, which was a normal average backdoor, supports command execution, file transfer, log tampering. But what is interesting, and again, another pattern, is the masquerading of VMware services. Another unique point, which I'll touch on in a moment, is the VMCI listening aspect or component of this backdoor. Secondly, we have Virtual Pi, another type of backdoor seen deployed as a vSphere installation bundle. This was Python-based and masqueraded as a VMware service and listed over IPv6. Lastly, the one that kind of sits in its own little wheelhouse is Virtual Gate. This was seen across guest machines for both Windows and Linux, and would act as something to interface with the VMCI listener of Virtual PITA. So drilling a bit more into the vSphere installation bundles, something you have to know about ESXi hypervisors is by default, the entire operating system is pretty volatile. What that means is if you were to write a file to your bin directory or etc directory in a Linux machine, you reboot it, it'll still be there. That's not the case on ESXi hosts. You're basically starting with a clean slate every reboot. To apply changes to this clean slate per reboot, administrators will utilize VIBs, or vSphere installation bundles, to basically facilitate software distribution and virtual system management. So broken down, we have your configuration file, which is an XML descriptor. We have your VIB payload, which is where they'll actually store the backdoors themselves, and a signature file, which in our attacker's case was either empty or filled with a false signature. Now, we were seeing the attacker deploy multiple VIBs to single hosts, or across multiple hosts, but multiple backdoors, multiple hosts. And since these are executed on every single boot, they're always available as long as the system is online. So once persistence is established, the threat actor has service level access to the hypervisor or the ESXi host. This is where the host to guest interaction becomes important. With the CVE 2867, the attacker is able to execute commands on both Windows and Linux guest machines without any authentication checks made on the guest machine level. This means that there will not be your 4624s on your Windows machines. This means there will not be the BTMP, WTMP, UTMP authentications on your Linux machines. The only thing you will see logging in by default is in your ESXi host itself. And this gave the attacker privileged access to kind of do as they pleased, execute commands, transfer files both onto the system and off of the system. And as we'll see in a moment, this gets expressed in a few odd ways that kind of ended up working on our part. So if we take a look at some of the guest interactions here, is this the correct one? Nope, my eyesight sucks. That's all right. In this case, we see one of the recon commands ran by the attacker from the ESXi host level. We have the e.py, which is for the exploitation, the VPX user, which is a service account for the ESXi host, the target guest machine, and the command that will be ran. And as I said earlier, the ESX host will log this under a VMware.log, which sits underneath that unique guest machine in the data store 2 partition. Unfortunately, with default configurations, we were unable to identify earliest activity that this type of exploitation was occurring, as a lot of the clients, it'll only last for a few months without extending the retention. And another important part here is that if the attacker has control of the ESX host, your traditional network segmentation for your guest machines will not stop the attacker from accessing them. You can basically disconnect all network adapters in your vCenter or ESXi solutions and still interact from the ESX host down to that guest machine. And therefore, it became your normal remediation actions of just having your EDR quarantine a host aren't going to work. So this was what I meant to do. There we go. As we'd see one more of the examples, this is actually the one that tipped off the start of all the investigations. As we'd see in both of these commands in the past one, the attackers love their lull bins. If they don't have to drop something on a host, they will not. And in this case, we got alerted on some credential dumping, and that led down the rabbit hole of where we are today. Additionally, we have make cab, that's some data staging. But again, stick to your native Windows binaries, and there's a lot less opportunity for detection. All right, so as I mentioned earlier, we have virtual gate and we have virtual PITA. Both of those were utilizing what's called VMCI sockets. VMCI sockets are kind of this oddity, if you will. They sit under a different address family than your TCP IP stack. VMCI was designed to enable quick and authentication-less communication between your host and guest machines, and kind of act as the backbone for a lot of the quality of life features that you expect, like copy and paste across your virtual machine and your host, file transfer back and forth. A lot of the backend runs on that VMCI, so it's kind of cooked into your KVM, your ESXi. Any type 1 hypervisor most likely utilizes this on the backend. And the attackers abused the hell out of this. On our end, we saw them deploying backdoors on the ESX hosts, and they would be able to connect in from these listeners. So as long as there was a backdoor on an ESXi host, any guest machine could directly access that backdoor, regardless of VLAN configurations, regardless of network segmentation, as it technically acts as an IPC within the hypervisor itself. Now, where this becomes even more concerning is, let's put 2 and 2 together. You have a guest machine, and or let's say you clean your entire environment, all your guest machines are reimaged, but you keep that backdoor on your ESXi host. If an attacker regains access to one guest machine on your environment, they can regain access to your hypervisor. From there, they can pivot right back into any other guest machine. Again, your VLAN configurations aren't really going to do you much good. And where this gets a little bit more frustrating is because it sits outside the TCP IP stack, your traditional NetFlow is not going to capture VMCI socket activity. There are specialized commands that you will need to utilize to even listen for this in the first place. So I'll pass over back to Brad for the key takeaways.
All right, so yeah, well, let's talk about some of the key takeaways that we've learned throughout these investigations, some things that we think various organizations can kind of implement from this, and kind of touch on some of the alerting and detection mechanisms available to us. So the first thing that we noticed, network segmentation and kind of restricting access to these edge devices and virtualization technologies. I think this kind of hammers home that point that it's so important to make sure that we are restricting access to these management interfaces for these virtualization technologies, our firewall technologies, and things like that, because the attacker is targeting these devices. Once they have a foothold on those devices, it's very hard to detect them. So making sure that we restrict access to only the administrators that need to analyze those or to administer those systems, as well as from the workstations that they're using to access those devices. And making sure that they're segmented properly from whether that's from the public internet making sure that only the services that they need to communicate with are available to those devices. Alex mentioned some optional logging that is available in hypervisors. There's also some additional logging that we found on Fortinet devices that we've blogged about in a couple of our blog posts related to this threat actor. Encourage the organizations out there to check that out, see if it makes sense for your environment, if it's something that you can enable and gets forwarded to your SIM just to have additional visibility. One of the biggest challenges with this threat actor is they are very good at covering their tracks. We have seen most of their backdoors have capabilities to disable logging services, and they're also very meticulous with how they clear logs. They will only remove events that are related to their activity instead of clearing the entire log. Alerting for those logging gaps and configuration changes. So we've mentioned that on firewall management devices, they were leveraging firewall management scripts to compromise the firewall fleet. So alerting on any time there's a configuration change may be something that's valuable for your organization, as well as logging gaps. So what we noticed whenever they would be active on hypervisors or on the firewalls is they would turn off syslog logging for the period of time that they were active. So if we're able to kind of see, why is this ESXi hypervisor not reporting any logs for several hours, or this firewall is not reporting logs for several hours, that could, be something worth tracking down and trying to get to the root cause of. The fourth bullet point here, network traffic plus firewall events. This was our biggest, log source or data source that we could use to kind of track this attacker activity. NetFlow was critical for kind of tracking the connections between the firewall management server to the firewall to the virtualization layer. And that's really, just so critical nowadays to have NetFlow logging in your organization. So, making sure that we have good NetFlow visibility in our environment. Firewall events as well. So the standard retention, I think, on a lot of firewall vendors out there is probably pretty limited. So making sure we forward that to our SIM, have a good retention period for that in case we do have to go back several months worth of events to kind of track down this particular activity. The fifth bullet point here, enabling secure boot. So one of the things that Alex mentioned was on the ESXi hypervisors, the attacker was abusing these VIBs to kind of have a persistent backdoor. Secure boot kind of helps us protect against that activity. So looking at our virtualization technologies, what are some ways that we can make sure that we're enabling all the security features to kind of prevent some of this abuse for these plugins or these VIBs. And FIPS compliance mode for your firewall management or your firewalls and your firewall management devices. What we noticed is that the attacker kind of shied away from those particular devices and mainly focused on the ones that did not have this FIPS compliance mode enabled. So definitely something to consider to kind of further lock down those devices and make sure that they're only running the application and software that they need to be running. And then aggressive patching lifecycle. We commonly saw the attacker targeting older versions of ESXi, of FortiGate firewalls and stuff like that. So just ensuring that your organization is staying up to date as much as possible with patching these devices because they are being targeted. And most of these do not have EDR solutions where we get that great telemetry to really kind of analyze and see what's going on. And I think with that, that is our presentation on UNC3886, and we'll open it up to questions.
Any questions, just raise your hand and I'll come with the mic. The guys will also be available after the session if you'd like to have a more in-depth chat.
Thank you for that. That was amazing. Great job, guys. I did have a question. From a customer standpoint, if we have been following actors that may use similar TTPs, is there any similarity to previously observed actors that Mandiant has seen in UNC3886?
Unfortunately not. At least not that we have strong enough ties to make solid attribution towards. While we know from a range of indicators that they are Chinese espionage, unfortunately, they're sticky in the UNC group for a reason. Until we have more casework or more evidence, I guess, to suggest that they can be tied together. That's kind of where they sit.
Okay. Thanks, Alex. Thanks, Brad.